Recording's rolling. It is Tuesday, September 30th. Right, so this was fourth period, and what you guys told me you wanted to do is my earlier class, I went through about half of the recommended puzzles. Right, so we're going to pick up from there. So I'll give you guys a brief recap of the ones I went over this morning for my first period class. Right, and then I'll pick up, well, last one I left off on was this number 23 here, right here. Right, so what's a recap so far? Okay. So there's this number 9, a salvaged boat uses a winch to pull up some treasure. Pull up some treasure. Okay, so the treasure question. Uh, there we go. Okay. Looks like this. Okay. Right, so there's this box of treasure. All right, we're pulling it up. There are three forces on the treasure. There's this tension in the forward breeze to pull up the treasure. Okay. The treasure has some weight, and also there's guys, if you're dragging this treasure box up, this is like a resistive force from the water. Okay, so don't miss this one here. There's actually a third force. Okay, the water's pushing down. Now, since these two are pointing in the same direction, what you can do is you can put a little side notch and then put that force going down, so it's really obvious that there are two downward forces. You guys see that? The weight, but also the drag force from the water. Okay. Hey guys, once you know identify the forces, can you find the net force by sort of subtracting them, like one up minus the two down? You can find the net force. Once you find the net force, if you divide by the mass of the treasure box, you can find the acceleration. And then there's a follow-up question that says something about like how far has the treasure moved in some amount of time. And wouldn't that be a kinematic question? So you could apply one of those kinematic formulas. I think it might be. Well, okay, here, take me. That's it. I don't see it, but actually, no, it's somewhere there. Correct. So once you figure out the acceleration, you guys can figure out how far it's moved in some time interval. You can do that, right? So oh yeah.
I had a question. Would you review number 26 on the next page?
26 on the next page.
Right after 23.
Oh, this elevator. Yeah. Yes. In fact, I'll recap that with you guys too. Right. So I'll eventually get there. Number 5 here. There's these ropes. Right. And the deal with the ropes is right. This box is hanging here. Right? This box hanging here. There are three forces on this box. There's a force straight down. There's this tension up and to the right, and there's a tension to the left. You get that? Right, so that's the free body diagram. Okay. Now, I'll introduce a Cartesian system. Now, two of these forces, the weight and the horizontal tension, are already aligned with the Cartesian system, but not the diagonal. The diagonal I split the components. Isn't this like a sine component and a cosine component relative to this horizontal angle from the horizontal? Is it? Okay. And then your conditions are the forces in the vertical and also in the horizontal each have to sum to 0. So then you can navigate from there. You can figure out exactly what is tension 1, which is this one here, what is tension 2, which is this one here. Okay, is that? And there's an extension question that says, well, what if you change this angle? Okay, what if you change that angle? Right, so again, that's in the well, if you want to think about that, right? It's in the first period video, so you can watch that too. Right, but I think, what if I change that? What would happen to tension there? Okay. Okay, then number 11, we got a car going at 14 meters per second, and it brakes to a stop in 3 seconds. And we got a driver with mass of 52 kilograms. So what's the force of the seatbelt on the driver? So here, there's a kinematic connection. Actually, you start out with kinematic. Say, initial velocity is what they gave you, and final velocity must be 0 because it comes to a stop. And it all happens in 3 meters. You can solve for acceleration using the third kinematic formula. Here's the acceleration. Okay, is that about 3 g's worth, right? Because every g is like 10 meters per second squared. So it looks like about 3 g's, a little over 3 g. Okay. And then what force from the seatbelt on a 52 kilogram person? So you run over to Newton's second law of motion. You plug in the mass of the person and the acceleration, which is right here, and you can get the force. Okay, that's it. Okay. So that's all on number 11. Okay, so you guys get that? Right, then next page. Right, number 26, the elevator. Yeah. So this guy in the elevator weighs 700 newtons. Now, my first thought is I really want to know this person's mass. So if I estimate gravity being like 10 meters per second squared, which I usually round it to that, because if you weigh 700 newtons, what would your mass be? Yeah, 70 kilograms, right? So that could be useful to know, right? Know their mass. So let's call this a 70 kilogram mass person standing on a scale. And if the elevator's at rest, the scale reads 700 newtons because they weigh 700 newtons. Right? But what if the whole elevator starts accelerating upward? Right now, the reading on the scale is going to increase. Now, what did they tell you here? Okay, so they gave you different scenarios. One scenario is, what if the acceleration is 3 meters per second squared? So over here, I have a derivation. Figure out what's the normal force reading on the scale as a function of the acceleration. So it goes like this. There are two forces on this curve. Right, so the net force would be the difference because one force is up and one force is down. Wouldn't that be the net force? Is the difference between the normal force up and the weight down? Right? And that net force results in mass times acceleration. That's Newton's second law of motion. Guess it? So then if you're solving for the normal force rating, which is again the reading on the scale, you just very simply add over the weight, and that would be mg plus ma. And if you like, you could factor out the m. So go like that method. Now that is, I've seen that so many times teaching this class year after year. I mean, this is a new textbook, so it's like, wait, it's not a new question. It's one of these questions that comes up routinely. Right. I turned that into a poster, so that's a poster right there. It's in your thumbnail notes. Let's go back. Right, so there's normal force reading as a function of the acceleration. And sometimes you're asked the backwards version. Like sometimes you're told the reading on the scale, and you're asked what acceleration would produce that normal force reading. So could you guys extract A out of this if you had to solve for A? Right. And in this form, you're sort of given A, just like they did in the textbook. Okay. Guys, what about question C? It says you cruise upward at a constant velocity of 4 meters per second. Guys, if you're going upward at a constant velocity, then what would the reading be on the scale for this guy? Yeah, it would be exactly 700 newtons, wouldn't it? Okay. And it doesn't even matter what the speed is. Because what if you're going twice as fast, but still constant velocity? Yeah, it's still the same reading. Right? And this guy has no idea how fast he's going because there's no way to tell inside the elevator, right? Unless you account for all the acceleration of the point. Okay. All right, so you guys go with the elevator? Okay. Again, if you guys want to see a more in-depth, slower version of this, it's all in that first period video. We got okay, and then the skier. The skier is basically a zero friction incline. So they tell you the angle is 18 degrees, but they give you, and you're asked what's the acceleration, and then how fast would you pick up to after some time interval, right? Which is a kinematic connection after you find the acceleration. Okay, so this goes like this. So there's no friction, which means there's only two forces on the skier that block to be the skier, right? There's the person's weight, mg, and there's this normal force, like the support force from the surface, right? But that's it, because there's no friction, right? Now, for any incline question, I'll always introduce a Cartesian system that's parallel perpendicular to the surface. Yeah, go ahead.
Yes, on 26, you must.
What's that?
There was E on 26.
So back to the elevator question. Okay, so question E on 26. Yeah, let's go back to the elevator. Okay, guys, if the elevator is in free fall, okay, that's like this right here. Okay, guys, if you go into free fall, what does it feel like inside the elevator? Does it feel like you're in space? Okay, is everything just floating around? See everything's floating around like you're in the International Space Station? Okay, and so what would the reading be on the scale? 0 newtons. Okay, and how it connects to all of this, right? So I did the derivation for accelerating upward, but if you did accelerating downward, would it be like g minus a? Okay. And then if you're accelerating down like pure free fall, wouldn't this be g minus g? It's get g minus g. Hence, g minus g is up to 0. Okay. So the scale points 0. Okay. Okay. Then, okay. So the skier right here. Yeah. Now, if you break this weight into components to align with this rotated Cartesian system, then this, guys, what's this one here? Is this sine or cosine relative to this angle? Yeah, cosine, because it's adjacent to the angle. That's a cosine. So you take weight times cosine of the angle, right? Right. And that's exactly equal magnitude to this normal force. So this normal force is also mg cosine theta, right? Now, for this particular question, that ends up not really leading to anything. But if there was friction, you would have to know this because isn't friction force equal to coefficient of friction times the normal force, right? So it could be useful if there was a friction. But in this case, kind of a dead end. Right? What you do care about for sure is this component down here, guys. Is this component a sine or a cosine? Sine. See how it's opposite of that angle theta, and those are the same angle theta, right? That's 18 degrees. That's 18 degrees. Okay. So this is mg sine theta. So when you go kick over to Newton's second law of motion, in place of net force, this component right here is the net force. Isn't that mg sine theta? Right. And then divide out the mass of the person. And oh, look at that. There's always the acceleration on a frictionless incline, or in this case, the skier going down with negligible friction. Okay? Notice the mass of the skier ends up canceling out. Now, if you plug in numbers from the beginning, then that would be fine too. Right? Because they did give you a mass of the person, but it turns out even if you didn't know the mass of the skier, the answer is the same. So, guys, what if the skier had a bunch of friends, and all the friends had different masses? Right, you got somebody who's 50 kilograms, 60 kilograms, 70 kilograms, whatever, right? They're all different masses. Do they all accelerate together side by side? Yes, they do, because the mass canceled out.
Yeah.
Okay, so they're all accelerating the same. Right, yes, it. Right. And then, okay, you guys good with that so far? Okay. Then, you could answer any kinematic follow-up question, because if they start from rest, and you know acceleration, because acceleration, starts up in acceleration shows up in all three of these. Right? You could answer how far have they skated as a function of how much time has passed. So, like, if 5 seconds have passed, how far have they gone down the incline? Right? You can answer how fast have they gone as a function of time. So, 5 seconds have passed, how fast have they picked up to? You could also answer the question how fast they picked up to as a function of distance. So, suppose they skated down 100 meters, how fast are they going? And that could be the third one. So, any of those questions framed any of those ways, you could answer with one of those three questions. Right? You guys get it? Let me ask one of those there. All right, so that brings us to then the bell was ringing, and so all that's in that beginning video. Okay. So if you want to pick up from there, then whatever the timestamp is on this video, pick it up. So number 1 on this third page. Right, you guys ready to move on to this one?
Mhm.
Right, everybody? All right. It says a student exerts a horizontal force F on a stationary block, mass 2 kilograms as shown. The coefficient of static friction between the block and the floor is 0.75. The coefficient of kinetic friction is 0.45. Ooh. So if magnitude of horizontal force, that's the only force they show, but of course there's other forces going on too, is 10 newtons, then what's the acceleration of the box? And then later on, if the horizontal force is double to 20 newtons, what's the acceleration of the box? This reminds me of a question I threw you guys a few days ago. So remember the process is, I want to see if that initial smaller force is enough to overcome the initial static friction. And guys, if it isn't, guys, if this initial force does not overcome the initial static friction, then what would the acceleration of the block be? Yeah, it would be 0. Right? Or if it does overcome the static friction, then you have to move over to kinetic friction, and then there would be some kind of acceleration. Okay. So let's try this out. I've got here. So it's number 1 on the third page. I've got a block here. Got a block. Okay, so you have enough space around the block where you can draw a number of forces. Okay. So there's an applied force. A little side thought here. You notice that in the last few days, I've actually got 2 different shades of pink. So I bought a whole new box of this one, which doesn't really show up very well on the camera, I'm realizing. So I put those around. If you guys want to steal those, then that's fine, because you're not really going to use these. Okay. But the darker pink actually works pretty good. Okay, so they told you guys the mass of the block is 2.0 kilograms. Okay. So this block definitely has a weight. Hey guys, what's the weight of the block equal to? Yeah, about 20 newtons. I'll just call it 20 newtons. Okay. And since the block is on a horizontal surface, then which way is the normal force point? Yeah, straight up on a horizontal surface. That would be true. Okay. And since there's no other vertical type forces, then what's the magnitude of this normal force? Must also be 20 newtons. So that this, here's how I know that. I know that the sum of the forces in the y direction goes to 0 newtons. Right? That's how I know that. So 20 up, 20 down with 0 up. Okay. Initially, so this is for question A, the applied force starts out, here, I'll write some other givens. There's coefficient of static friction, they told you was 0.75, and that's a unitless value for newtons per newton, if you like. And the coefficient of kinetic friction they gave us 0.45. Right. So these would be like givens. All right. Anyway, there's a horizontal force of 10 newtons. That's it. That's what it was. 10 newtons. Right. So I'll go to the right. I'm pulling with 10 newtons of force. So I'll say like F applied equals 10 newtons, the applied force. Okay. Oh, do you guys see how I drew this arrow as half the length of the other 2 arrows? You guys that? because it's half the magnitude, right? 10 compared to 20, you guys see that? Right, so it's like half as long. So if you're drawing everything to scale, it's good. Okay, right. Now, I know for friction, guys, friction force, if it's a static friction force, right, that could be less than or equal to coefficient of static friction times the normal force. Wouldn't that be true? Okay. And notice it's an inequality because what if I put on a 1 Newton force? Now, 1 Newton force, that's really, really tiny. So when the corresponding friction force also respond and also be 1 Newton. Right? And then what if I double that to 2 Newtons? That's still a small force. So, no way is that going to overcome the friction. Okay, anyway, I keep increasing the force, keep increasing. Doesn't that static friction also continue to increase? Right? That's why this can be less than or equal to static friction times normal force. Right? I wonder how high the static friction would have to go before I finally broke the static friction. Let's find that out. Right, so I'll call it static friction max, like maximum static friction equals, right? We'll see how hard do we have to pull horizontally before we finally break that friction. You guys got that? Okay. So what do I plug in right here? 0.75. Yeah, 0.75. Okay, newtons for Newton if you like. So, right. And then, what do I plug in for the normal force? 20 newtons, because that's the normal force. Okay, normal force. Guys, what is 3/4 of 20? 15 newtons, 15, right? So what that means is the static friction force is allowed to go up to 15 newtons. Okay. And I'm only pulling with 10. So at this point, what is the friction force equal to?
0. No.
How about 10? 10 newtons. Right? So that static friction force is 10 newtons. Right? And what if I pull a little harder? What if I pull with 11 newtons? What would the static friction be? 11. What if I pull with 12? What's static friction? Yeah, thank you. Can't that just keep continuing? Because what if I pull with 14 newtons? What's the static friction?
14.
14. What if I pull with 15 newtons? What's the static friction? 15. But at that point, guys, once I start pulling with 15, I've sort of like maxed out the static friction. If I pull like a smidge harder, like like if a little bit of skiing comes on, right, that's it. The whole thing starts like sliding. Okay, so I can go up to 15. Okay. But at this particular snapshot, is the block still at rest? Yeah, block's still at rest. Block's still not moving. So what did they ask for acceleration? Yeah, they said what's the acceleration of the box? Right. Well, the net force would still be 0. So for A, the acceleration is 0 meters per second squared. Okay. Effective velocity is also 0. So both the velocity and the acceleration, they both zero out. There's no motion at all. Okay, so we're pulling, but the block's still stuck to the table. Right, here's the table. So, is that okay? Right. But you know that once I pull any harder than 15 newtons, the block will break the static friction and it'll slide. Now we're over to a kinetic friction case. Isn't that true? Okay. Which brings us to question B. So question B says F applied, we're going to bring it all the way up to 20 newtons. Okay. Actually, I'll go ahead and redraw the diagram. Is that okay if I start a new paper? Yeah. Right, so let's do, this is number 1B. Okay. Because the diagram looks a little different. Well, some parts are the same, some parts are a little different. Block. Okay. So the weight's the same as before. It's 20 newtons. The normal force is the same as before. Also 20 newtons. Okay. But now the applied force is different. Now we're applying a force at 20 newtons. A force applied also equals 20 newtons. Okay. But the friction force, this over here, force friction, is equal to coefficient of kinetic friction times the normal force. Okay. So you guys do know we would be in a kinetic case because I'm pulling so hard that now the block actually is sliding across the surface. Okay. You guys okay so far? Step by step.
I didn't really get how you got the first answer.
Okay, great. Okay, so little recap here. Okay. So I was looking at the static case right here. Let me see if I got a friction pressure. Yeah. Okay. This would have been helpful. Okay. This is helpful right here. Okay. So the static friction can go up to a point where well, you guys know static friction applies when the block's not moving, right? It's like kind of stuck to the table initially, right? And the coefficient of static friction was given as 0.75, right? So I need like some minimum applied force before it breaks that initial friction. Like how much force do I need? So I just pulled up this expression right here. I said like how high could the static friction go up to? Okay. Well, if the coefficient of static friction is 0.75 and the normal force is 20 newtons, the static friction can go up to 15 newtons, right? Okay. So I can pull up to 15 newtons, and I have not broken the initial friction, so the box is still stuck to the surface. Yeah.
Why can it go up to 15 newtons?
15? Because it's 0.75 times 20,
Oh, okay.
right? So 0.75 is the coefficient. Okay. 20 newtons is the normal force. Okay. So that I can pull up to 15 newtons, and the friction force will automatically respond. Like here in this picture, I'm only pulling with 10. So the static friction automatically responds, and it also matches at 10. Okay. Do you guys see there's zero net force? If there's zero net force, there's still zero acceleration anyway. But the block isn't even moving, so there's definitely zero acceleration. Okay. Okay.
So like if you plot it with any force up to 15, the block will stay there because it's pulling back with you. But if you pull 16 newtons, then you overpower the friction and start sliding into a
Exactly. Yeah. This applied force can go up to 15 newtons, and the answer would always be the same, 0 meters per second squared. As soon as you pull with like 15.1 newtons or anything above that, yeah, then we're gonna kick over to a kinetic case. Yeah. Right?
Okay, so in the case of the first one, it would not move.
Right. Yeah. So scenario A, which is this right here, the acceleration is 0 meters per second squared. Right. Velocity is also 0. Right. But now we're over to scenario B, where we've doubled the applied force to 20 newtons. And 20 is definitely more than 15 newtons. So now we're over to a kinetic friction case. Now the coefficient of kinetic friction is always less than that of static friction. Okay. So 0.45. So right here, plug in 0.45. Actually, just 0.45. Okay. Just a coefficient. Okay. And the normal force, well, that didn't change. That's still 20 newtons. Okay. Ooh, guys, what's 45 times 2?
90.
90? Ah. And slide the decimal around a little bit. Okay, so like 9 newtons. Okay, 9. So this friction force is now F sub F bar only 9 newtons. 9 newtons of friction. Right, you guys see that? Now, that's kind of interesting too, because initially we were pulling with 10 newtons and the block wouldn't even move. And now anything over 9 keeps the block in motion because it's a different kind of friction. It's kinetic rather than static. A little side top there. So that's the friction force. But the question is, what's the acceleration? So guys, anytime you have forces and a mass, relabel the mass. You guys remember the mass of the block was 2.0 kilograms? Okay. And you're asked for acceleration. You need to pull out what law of motion? Second law. Right, so now we're going over to Newton's second law of motion. Newton's second law. So I'm saying the acceleration is the net force acting on the mass. Right? Net force over mass. Which is, so big old fraction here. No, vertically the force is 0 out. Right, so I knew that from before. Sum of forces y goes here, right? But in the x direction, there is a net force. Guys, what's the net force in the x direction? 11 newtons. Because it's 20 newtons minus 9 newtons gives you 11 newtons. There's an 11 newton net force. Right? 20 to the right, 9 to the left. Like I said, that's acting on 2 kilograms. Okay, just like that. Better? So I have 11 Newton net force acting on 2 kilograms. So what's the acceleration? 5.5 meters per second squared. And then that's to the right. Because it's maybe to the right. So a little direction right there. The vector, grab direction. Yeah.
The answer shows we have 5.6.
Okay. Okay, yeah, they gave you a multiple choice and it's 5.6. Right, they probably used 9.8 meter per second squared for the gravity field, and I used 10. Right. So if it's off like a tiny bit like that, that's probably why. Yeah.
Thank you.
Yeah, so that's a good thing to point out too. Yeah, I didn't realize that was multiple choice thing. Yeah. All right. Here we go. Boom. Okay, you guys ready for the next one? Next one. There you go. Okay. Boom, boom. All right. Ooh, we are on the back page. Okay. Ooh, hey, look at this. It's one of these incline atwods. One of my circle. Yeah. I'm seeing, of course, a bunch of fun ones to skip too, but let's do the circle ones. Got two blocks connected by a like string. Assume the string does not stretch and also has negligible mass and friction, as is this pulley. There's negligible mass and friction on the pulley right there. Hold it. Okay. Block one on the incline 1 kilogram, and block two it's saying over here has mass of 0.4 kilograms. This angle is 30 degrees. Coefficient of static friction, coefficient of kinetic friction, 0.5, 0.4. What's the tension in the string? Okay. So I'm kind of curious to know. I wonder if it's like not moving at all. In which case, I think the tension would just be the weight of the hanging block, right? Or maybe it is sliding. And if it is sliding, which way is it sliding? Right. So we got to figure all that out. So kind of like picking up from the last question. We'll have to check and make sure it's broken the static friction first. So 19. We got here. I'll say given. Let's put the givens right here. Mass 1 is or has okay 1 kilogram. Mass 2 is 0.4 kilograms. Theta is 30 degrees. Coefficient of static friction is 0.5. Coefficient of kinetic friction is 0.4. Right? I think that's all they gave, right? Okay, I'm going to throw in one more value. Let's have G equals 10 meters per second squared. Again, if you do 9.8, the numbers are going to be slightly different, but probably not significantly different. So there. So let's go with that. Those are givens. Okay. I want to know what's the tension in the string. So let's draw this out here. Okay, so fully up here. Okay, this block. Oh yeah. Huh? You guys alright? Over here. Connected by a string. Okay. Okay, so something like that. So this mass is 0.4 kg, and this mass is 1.0 kg. This is 30 degrees. Okay, I think that's what we're looking at, right? Something like that. Okay, let's get a three-body diagram going for these blocks. Now, I know that the one on the incline, I want to think of in terms of this rotating Cartesian system, so I'll go ahead and set up some axes, like dash off some axes here, like x-axis, y-axis that are aligning to the surface. Okay, so same thing. Okay. All right, let's get some force vectors. Right, so this one on the surface has a weight and doesn't Earth pull it just like straight down towards the center of the Earth. Okay, and that weight right there is equal to how many newtons about? Gonna be a 10 Newton weight right there. 10 newtons. Right. But what about this one over here? What's this weight over here? Would that be only 4 newtons? Right. 10 newtons down here, 4 newtons here. Is that right? Okay. Now, which way would this actually want to rotate? Does it want to go more clockwise or more counterclockwise? Like, for example, what if there was no friction at all? No friction at all. Okay. Now, for that, I need to compare like components. So I'm going to break this 10 newtons into components. Now, there's some other forces I have to draw, but I'm going to break some of the components first to figure out everything else. Guys, notice right now, guys, how am I holding my ruler? Is my ruler parallel to the ground or parallel to the surface of the incline? Surface of the incline. And you guys are doing the same thing? Okay, as you're dashing off these components. This is still 30 degrees here. Right, so that's okay, right? We got. Now this component I know is 10 newtons cosine 30 degrees. This one would be 10 newtons sine 30 degrees, right? In fact, guys, 10 newtons sine 30 degrees, I bet you guys know what that is. What's sine of 30 degrees? Half. Yeah, what's half of 10? This right here is 5 newtons. Right? It's like pulling down to the right with 5 newtons. Right? Now the cosine one, I should know. 10 cosine 30. Yeah, like 8.66. Okay. Which is important because it'll help us find the normal force, which will also later on help us find the friction force. Let's go ahead and draw the normal force here. Normal force equals 8.66 newtons. Okay. Right, all right. Because it matches this, and that's 10 cosine. There. Right, okay. 8.66 newtons. Right, guys, where? Now, suppose for a moment that there was no friction. Like, what if these coefficients of friction were equal to 0? If this is all 0, then which way would this want to move? Clockwise or counterclockwise? Huh? Okay, show of hands. How many guys say clockwise like this? Who says clockwise? Yeah. Because, and how do you know? Because 5 newtons is more than 4 newtons. Get it? And in a tug of war between 5 newtons this way and 4 newtons this way, overall, it would be moving this way, wouldn't it? Okay. Which, or if you had a really heavy block hanging on the left side, the answer would change the other way. Right? But this way it wants to go clockwise. Do you guys see that? Clockwise? Which means that the friction force on this block is pointed which way? Up and to the left or down to the right? How many guys say up to the left? Who says up to the left? Up to the left. Yeah, winner. Because remember how 5 newtons beats 4 newtons, and this whole thing wants to go clockwise? And doesn't friction resist that motion? So friction is going to point up to the left. Okay. But how much friction? I'll just draw a general arrow up and to the left. Okay. How much friction there is depends on these coefficients. Right? Now, guys, look at coefficient of static friction. See, it's like 0.5. That's pretty big. That means static friction. So friction, static. I'll say if it's static friction, couldn't it go up to coefficient of static friction times normal force? You guys remember that? That comes from this right here, right? Okay. Hey guys, what's the normal force equal to? What number? 8.66. You guys see that? 8.66? Okay. And if static friction is 0.5, which is like half, guess what's half of 8.66? Is that 4.33? 4.33? Okay. Now, this friction force is not 4.33, but it can go up to 4.33 newtons, couldn't it? Okay. But it's not going to. Guys, what's this friction force actually going to go up to? Because, guys, if it was 4 point something, there'd be like so much force pulling this way that the whole thing would actually turn around and accelerate that way, which it couldn't because that would reverse the friction direction. Okay. Yes, this is going to be 1 Newton. 1 Newton. Do you see that? Okay. Like, looking at these external forces, there are basically 3 sort of external forces or components I care about. I care about this weight. On the left side, it's 4 newtons. I care about this component over here, it's 5 newtons. And I care about this friction. And this friction can go up to half of 8.6. It can go up to 4.33, but it's never even going to reach that. It's only going to go up to 1. Because if there's 1 Newton this way, plus this 4, doesn't that bring it to 5, which cancels out with this 5? You guys see that? Great. Do you guys follow what I'm saying? Great. Here, I'll say it again. Great. So if there's no friction, there's a tug of war between this 5 and this 4, and the 5 wins and it slides this way. But there's a lot of static friction here, or there could potentially go up to 4.33, like half of the normal force. Half because that's what 0.5 is. Okay. But you don't even need that much to bring this whole thing to a stop. All you need is like 1 Newton to bring it to a stop. So that's what it's going to be. This friction force is 1 Newton. You guys see that? Okay. So Guys, if that's true, here, I'll go ahead and label that. Call this 1.0 Newton. Right. F friction static max could be 4.33 newtons. Because this 0.5 could have been right there. This normal force. Right there. That's where I'm getting the 4.3. But it's only 1 newton. So if you guys see this whole thing is just gonna be at the top. Therefore, what's the actual acceleration? 0. Right. So the answer is 0. Which I don't know, that's not very exciting. So what about this? What if we got rid of all the friction and we answered the question from there with, oh, sorry, that wasn't the question though. The question was what's the tension and the strain? Let's answer that first before I change this up. Guys, if this whole thing is just stopped, it's not even moving, then what's the tension and the strain? It's stopped, it's not moving. I'll give you a hint. You can very quickly get the answer if you just focus on the hanging block. If that block is just sitting at rest, 4 newtons. Yeah, 4 newtons. Because it weighs 4 newtons. So it doesn't have to be a 4 newton tension to hold it in place. And there's only one tension in the string. When that tension also be over here is 4 newtons. Right? In fact, if you just focus on this block, you could have gotten it 2. Because guys, what's 4 newtons up to the left plus 1 newton up to the left? What's 4 plus 1? 5. And does that cancel out this 5 pulling down to the right? It sure does. It's the same thing. You see how it all zeroes out? Right. So no matter how you look at it, the acceleration of the whole system is 0 meters per second squared, and the string tension is 4 newtons. Okay, that's the actual book answer. Okay. Right, guys good? Okay. Right, now, if this were to show up on a quiz, it probably wouldn't do that. I might say either make these frictions a little tiny. Let's just get rid of friction. Right? Because what if there's do I want to do that? Let's do how about this? All right, I'll just instead. I'm gonna make one of these blocks really heavy. Okay, you guys want to do that instead? Let's make one of these blocks really heavy. Otherwise, we'll leave everything the same. So I'll call mass 1. How about I'll do let's make it like 5 kilograms. Okay, and I'll leave everything else the same. Mass 2 is 0.4 kg. Let's have the angle the same. Let's have the coefficient of static friction the same. The coefficient of kinetic friction the same. And let's use the same gravity as we were using before. Okay, so these are my new given values. Okay, right, so really all I did was I just changed this mass 1 on the incline and make really heavy. Right, so that we'll get this whole system in motion and it'll just be a little bit more exciting to work with. Okay, so in that case, okay, I'll run through this one a little bit faster because the book doesn't actually ask it. Okay, but I'll show you guys how you can do this. Okay. Okay, so dash off some components, just like before, or some axes, I should say. Some axes. Now this time, this is a huge weight. This weight is, well, if it's 5 kilograms, 5 kg, would this be 50 newtons of weight? Okay. And this little guy here, 4 kg, or sorry, 0.4 kg, has 4 newtons of weight there. Okay, if this is 30 degrees, this is 30 degrees, component, dash. Okay. The sine component, so half of 25 newtons is 25 newtons. Cosine, what's 50, cosine 30 degrees. This comes out to 43.3 newtons, which means the normal force is also 43.3 newtons. Okay. Now, guys, would this whole system definitely be sliding clockwise? Because this is such a heavy block here, right? Definitely going clockwise. So friction force is still pointed up and to the left. Okay. But how big would this be? Well, now it's going to slide over to the kinetic cage just because it makes it big. So I'll say the friction force equals the coefficient of kinetic friction times the normal force, which is this 0.4, 0.4 times this 43.3 newtons. Okay, so times 0.4 is like 17.3 newtons. Okay, that's your friction force. So that's this one right here is 17.3 newtons. Right, you guys see that? That's friction equals. Okay. Now, at this point, there's three main driving forces that I care about. Here, I'll circle them in blue. So I got this 4 Newton saying, let's go counterclockwise. And the friction, okay, this weight component said, no, let's go clockwise. In fact, this one's so big, 25 is so much bigger than 4, it's definitely going to be winning. So the friction force is going to try to slow everything down, say, no, and pull back the counterclockwise way. You guys see that too? Right? Now, guys, what's the net force on the whole system? What's the net force? I'll say F net for the whole system. Wouldn't that be 25 newtons minus 17.3 newtons minus 4 newtons? Do you guys see that? Is that? Okay. Which would be, let's see. Okay, I got 17.3 right here. So it's 25 minus that, minus 4. Okay. 3.7, I'll call it newtons. 3.7 newtons. Okay. That's the net force. Okay. And if that's the net force, can you find the acceleration? Guys, if you know net force and you know mass, how do you get acceleration? Newton's second law. So acceleration is net force on mass, which in this case is 3.7 newtons net force. 3.7 newtons. And, ooh, can I add these together? 5 plus 0.4 kilograms. Okay, so 5 kilograms is plus 0.4 kilograms. So the acceleration is 3.7 over 5/4 is 0.69 meters per second squared. Okay, that's the acceleration. Last question is, the book was sort of orienting this towards what's the tension in the string. So I can still find that too. Right, you guys ready to find the tension in the string? Okay. So tension of string, I can either focus on just this block over here or just this one. And guys, which one do you think is easier to work with? The inclined block or the hanging block? Yeah, definitely the hanging one, because there's only 2 forces on it. Okay. So I haven't even labeled the tension yet, because that's just internal to the system. But now I can think of it like acting on this block. So I got 0.4 kg. I know there's a down force of 4 newtons. 4 newtons down force. And there's an up force of some tension. I'll just call it T. And that's what I'm solving for. Get that? Okay. Now I can go through Newton's second law of motion as it applies just to that hanging block. True? They say F net equals ma. Okay. And F net is the difference between the tension pulling up and the weight pulling down. And I know the weight down. That causes a 0.4 kilogram block to accelerate at, where'd it go? There it is, 0.69 meters per second squared. Okay. So that's 0.69 meters per second squared. Okay, so add over 4 newtons. So that number times 0.4, then plus this 4 newtons. So the tension of the string would be 4.27 newtons, 4.3 newtons. Okay. So again, that's just an addendum where I changed the numbers a little bit just to put it in motion and then answer the question. Right. Okay. All right. Let's see. Oh, guys, let's do this because we got about 4 minutes. So I'll walk you guys verbally through these two right here. Okay. So do you guys see this one? There's a block. They give you the mass of the block and an initial velocity, and they tell you some distance from the edge of the table. Actually, sorry, they want you to calculate the initial velocity. So if they want you to calculate the initial velocity, okay, they told you the height of the table, they told you a coefficient of kinetic friction, and they told you where the block lands. Do you see you have to solve this whole thing backwards? Do you see that? The question is what was happening right at the very beginning. So you have to solve the whole thing backwards. Can you guys solve this projectile to figure out the speed it was leaving the table edge? Guys, is that exactly the same as your projectile lab? You guys remember your projectile lab? Here, I got a poster for it too. I'm gonna find it real fast. Poster for projectile lab. It's this one. Aha! I found it. You guys remember this right here? You can find the speed that it's leaving the edge of the table based on where it lands and the height of the table and the gravity field. You guys remember that? There's a whole process behind it. You're looking at it right here. Okay? So you would solve this backwards. You figure out how fast is it leaving the edge of the table. Okay? Now, if you know the distance that it slides and the final velocity at the very end, because sort of call this final velocity leaving the edge of the table, can you solve for the acceleration. Can you guys solve for the acceleration using kinematic motion? Okay, so that sounds kinematic. Okay, here's your kinematic equations. So you need those. Okay, and then finally, there's one more that you need, and I'm gonna find it. Aha! I found it. I found it. Okay, it's this one right here. So you know the acceleration. You know the sorry, scratch that. Okay, you know the final velocity. You know the distance that it goes. You can find the acceleration like this. You know the coefficient of friction. You know the gravity field. So you can find the acceleration doing this. Okay. Okay. And then you can connect that over here. Okay. I know the speed it was leaving the table edge. Okay. I know the acceleration because I know this right here. Okay. And I know the distance that it looks. Actually, you use this third one. So here's the distance of slides. Here's the speeds leaving the table edge, which you found from this. Okay. You know the acceleration, which you found from this. And then you can solve for this initial velocity. You guys see that? Okay. All right, last one. Help you guys out with number 8. Model raindrops. Raindrops. So there's also good raindrop. They say model raindrop is here. Okay, so here's your raindrop. Raindrop. Number 8. And because what's the raindrop is reaching terminal velocity? Let's have a few raindrops. Let's have a little tiny raindrop, big raindrop, maybe like a medium raindrop. Okay. Terminal, guys, if it's terminal velocity, what do you know about the free body diagram? All the forces do what? Zero out. Okay. So this has a huge weight and a huge drag force. F drag. Okay. Maybe this has a small weight and a small drag force. And this has a kind of a medium weight and a medium drag force. You guys get that? Okay. Now drag force is proportional to well,
Oh, I don't.
here I'll say equals KAV squared. Right? Now, A is this cross-sectional area here. Okay. And guys, if the drag force is equal magnitude to the weight, can I effectively say the weight is also equal to KAV squared? They want to know what's the relationship between this speed and the radius. This radius right here, the raindrop. Guys, doesn't this mass occupy volume? So it's like 4/3 pi r cubed is the volume, and then multiply that by the density of water that gives you the mass. Then isn't this cross-sectional area like pi r squared? You guys see that? Yeah. So could you finish this and solve for V in terms of R? Okay. That'll get you guys started. All right, so you guys have a good night.